What we're going to do today, and who's ever going to come to next week, my passion is to take, first of all, I'm not a scientist, okay? I'm not a scientist. I studied science, I researched science, I'm up to date, but I'm not a scientist. So if there'll be questions I can't answer, I'll just tell you I don't know, okay? But I'm here to show you stuff and talk to stuff that I do know. And what I like to do during the years is to, because in the scientific, my professors and people I used to do research with, we get excited and there's so much amazement going on and new stuff, research, and a lot of the Joe public people like us, we don't get to really grasp what they're talking about sometimes. And what I like to do in my talks is take these in-depth scientific findings and bring it in a very, sometimes metaphoric way, very easy to understand way to grasp how amazing it is. I could just say that during all the years, the more I've studied, the more I've learned, the more I've found out, the less I know. So that's more or less what I'm trying to give you today. So today we're going to talk about planet Earth. Next week it's about going out of planet Earth into space. But this week, we're going to look at planet Earth from a very specific angle. We're going to look at it from the ocean floor perspective. Is that a good focus? We're not going to talk about the life on planet Earth. We're not going to talk about animals. We're not going to talk about the fish in the seas. We're not going to even talk about the water of the oceans. We're going to talk about the ocean floor in a very specific way and look at it in a metaphoric way in order to understand and to grasp how unique our planet is in terms of its dynamic life. The planet itself, the rock, not the life on it as such that we know a lot about, but more about the whole planet as an entity. And that's what we want to go through. And I am going to use, like I always do, some kind of metaphor in order to make it easy to understand. And we're going to use some kind of life story that we can all relate to as a cycle of our life. But first things first, let's see what we're talking about. So if we cut the Earth into the middle, we have the core that is usually known to be liquid. The crust is actually the plates that we're going to talk about today, and they float on the mantle. And we're only talking about this very, very, very thin layer, thin in terms of the vastness of Earth. When it's under continent, it can get nearly to 150 kilometers. I'm going to talk a lot of kilometers here and not miles today. Width. Under the ocean, it's very thin, and it's only 1 or 2 kilometers thick. And we're talking only about that crust on top. That crust is moving all the time, and they're called plates, and we're going to go into that soon. And the plates can move from a very slow pace of 1 or 2 centimeters a year, or 3 or 4, to some of them actually move up to 35 centimeters a year, which is unbelievably fast in geological terms. Okay? Because when we talk geological terms, we talk millions of years. This is dynamics of movement that are quite fast. The only thing that stays the same is the circumference of the Earth. The Earth doesn't get bigger or smaller. Okay? If it's a football or something, it will always stay that size, but things are happening in it. And you can imagine we're talking about an egg, whereby the yolk is liquid, and the shell is floating on it, and it's pieces of shell moving all together. What was the first thing that humanity kind of suddenly said, whoa, there's something going on here under the ocean, and probably we don't know anything about it. In 1872, they were laying the telephone line, the first telephone line, from Ireland to the North American part, literally going with a boat and putting it down on the seabed, and they knew that the seabed average depth is about 5 kilometers, and they were just doing this with this boat called Chanard ship. And then somewhere in the middle of the Atlantic, the cable didn't go down 5 kilometers, it went down only 2.5 kilometers. So they said, ooh, that's a nice big rock in the middle of the ocean, 2.5 kilometers high. Let's roll it back, and they went 50 or 60 miles south of that point and did it again, and the same thing happened. They did it 5 or 6 times. in a radius of about 100, 150 miles, and they always got to that 2.5 kilometer mountain. So they understood there's not one mountain, but there's a ridge. This is before they can even look down there or know what it is. Then in 1912, a scientist called Wagner, he came up with the idea, probably most of you heard of it, of Pangaea, the early continent that started to break up and spread around. Today, we know, of course, if that was the beginning of Pangaea, today we are here, and you can actually very, very easily see how the pieces of the puzzle come together in lots of the continents. But what Mr. Wagner did, he took fossils of creatures that are long deceased, distinct, and he took pieces from each continent, and he was proving that, for example, this one here, which is a Nestorius, it swims in rivers, but it can't cross an ocean. And the specific creature was here in the tip of South Africa and here on the tip of South America, in both different places, that it couldn't be swimming there. So, and by looking at this kind of research, he started to establish what we know today as plate tectonics. And in 1960, it became the official science of what's happening on our planet. These days, we use very sophisticated methods, which I won't go into most of them very detailed, but just talk to you about them, to prove and to see how everything moves. So seismic and sonar, the boats let down the sonar waves, and they have all kinds of detectors, and they can today map really, really specific features on the ocean bed 5 miles down, even more. And because they have also system and robotic systems on the floor bed, they can measure very slight movements and every kind of little thing that's happening there. So that's one method. The most common method today and the most precise is the geometric, which is done by satellite. So you have all these little devices everywhere that is needed, and they can track millimeters and millimeters of movement of huge tectonic plates and hills and cracks in millimeters, in years and decades and all that. So that's the most accurate way they're doing it today. This is a very interesting method. We won't talk about it right now. We'll talk about it in a few more slides, the magnetic way. So after all these research, and today we know exactly how the structure of the plates are. And these are the major plates that are under our feet. Okay? It's moving all the time. All the plate boundaries are moving and creating sometimes very specific life that we'll see a bit later, and just shaping our lives as humans on the planet for millions of years today and in the future. And you probably maybe heard of most of those plates, but these are the main plates that we're dealing with. So let's start looking at those plates, but from this unique angle of the ocean floor and this metaphor. The first one we're going to actually start with is not going to be from the beginning. In order to understand better how everything's working, we'll start from the mature plate, from the mature ocean. Our representative for the mature ocean is the Atlantic. And as you can see very clearly, we can see how this matches here, Brazil and West Africa, and how North America and this part of the Sahara mixed together. And it's very obvious how it moves. And we see on the ocean floor this great huge zip, which is actually that ridge that the cable from the telephone line couldn't go over. 2.5 miles, 2.5 kilometers high, this ridge goes and crosses the whole ocean from south to north. What happens there? It's actually where the plates are born. It's where the plates are created. In the middle of the ocean, there's a crack, and the mantle comes up, and lava comes out, and freezes, and not freezes, but cools down, becomes rock and basalt, and makes another layer. So if we zoom in to the crack, every layer just comes up, cools, becomes rock. Then magma comes up, pushes aside, becomes rock. Magma comes up, pushes aside. It's a conveyor belt, and the plates are getting built symmetrically to each side. That's what's happening. So if we look here, what's actually happening, this is all new plate that's being created and pushing Africa and America apart. And as you see also, there's lots of transfer faults and cuts because it's so rigid and there's so much activity going on there that the ridge itself is very fragmented, but you can actually see at the top of it there's the Mid-Atlantic Ridge Valley. That's where everything's happening and lava's bursting out all the time and all these faults in the area. Now, when you zoom in to this area, you see very interesting life forms that we didn't know exist. Before that, I did some DIY to show you maybe what I mean by new plates spreading. I'm very proud of this. So, if this is the mid-ocean ridge, yeah, this is the mid-ocean ridge. Imagine there's like a hill here, but what's happening actually is very symmetrically, the plates are being born. And if this side is America and this side is Brazil, from your point of view, yeah, that's right, they're actually pushing apart the continents. Isn't that cool? So, what we find in the mid-ocean ridges, and this is a huge piece of our Earth. It's more than nearly all the continents, this ridge, this everywhere in the oceans, in the middle of the ocean. We found these unbelievable, what's called black smokers, hot vents, everywhere. Not only the lava explosions, not only underwater volcanoes, but these things are so unique because around them, at 380 Celsius, live a whole species of life that we didn't know can exist. Okay? Life as we didn't know it. There's a word for that, it's called extremophiles. It's creatures that live not of photosynthesis and the sun, but from other things. In this case, chemosynthesis. They take the chemicals that come out of these rich, hot vapors, and they live off that. Okay? It's a huge world out there that was discovered when we went down to look at the mid-ocean ridge. And the green shows you where those unique life forms live. It's believed that there's more than 10 times creatures there than in all the tropical forests in the world. More than 10 times that, even more. And we don't know most of the area. We don't know most of the ocean. It's an unbelievable form of life, and this connects to next week's lecture, and I'll talk about that a bit at the end, because when we're looking for other planets with life forms, we're not necessarily now checking only for photosynthesis, we can check for life forms that we suddenly see that we have under our feet in the ocean. This is just a glimpse of other extramophile animals that we have all around us. This little nice creature is called a water bear. He lives in our puddles, murky puddles, and all kind of other creatures. We're not going to talk about them today. Maybe one day in a future talk we'll talk about extraterrestrial life on Earth. So, how did we prove, because we can see it here, and we see the movement, but how can we actually prove that it's actually spreading scientifically? And that's where the beautiful magnetic proof comes in. Some of you who studied chemistry maybe remember mercury, the mercury temperature of when iron atoms, when they start to go all over the place, it's 580 Celsius. But when it cools under 580 Celsius, when it cools below that, all the iron atoms start to stand and sit and line up in the direction of the magnetic field next to them, which on Earth is the North Pole. So, when we have liquid lava coming out of the mid-ocean ridge as iron in much more than 580 Celsius, it's just all over the place, the atoms of the iron. But the minute it cools down to under 580, all the atoms line up to the North Pole. So when we take pieces of stone lava, pieces of basalt from the mid-ocean ridge, and we look at it with microscopes and other machines, we can actually see that if you don't touch them, you just take them exactly how they are. They're pointing to the North Magnet Pole. Now, why is this so important? Maybe most of you don't know it, but every few hundreds of thousands of years, the magnetic poles reverses. So we are now living in an era whereby the magnetic pole is north. But if we were going around here, the Forest Row area, 200,000 years ago, and we took out our compass, it will point to the south. Because it changes. Humanity doesn't know why or how. It's to do with the inner core, it's to do with some kind of dynamo effect. But the magnetic pole reverses every couple of hundreds of years. But that's great for our purpose. Why? Because if we drill on each side of the oceanic ridge, or even take the pieces of basalt that are lying down there, the stone, but from exactly the same place, symmetrically, we get a pattern. So black is the North Pole as it is today, in the north, and the white is when it used to be reversed. And if we look at 3 million years, for example, so this is the mid-ocean ridge in the middle, and we take samples from each side, we see the beautifully symmetric unveiling of this conveyor belt. And we can see exactly how the North Pole and South Pole have flipped sides, and that shows us how the ocean floor is spreading. And back to my little school DIY, now you see the little pieces of the little stripes here, so that kind of indicates how it's symmetrical. So every time the magnetic pole changes, we see it exactly. And because of that, we could now map all the ocean floor exactly and the age of it. So we know exactly that on the ridges, that's the youngest plate age, and as we go further towards the continent, it's the oldest, and we can do that in all the oceans in the world. So that's a beautiful way of how to prove it. And this is a beautiful story that I love. Ascension Islands. They're here on the ridge, and they're 2,300 kilometers away, and there's this green turtle that his habitat is on the shores of Brazil, here. But then he swims a few times in his life a round trip of nearly 5,000 kilometers to lay his eggs on that island. And today scientists understand that the ancestors that are more than 70 million years old of this turtle used to go to it when the island was very close. And the ancestry instinct, these turtles are keeping going to the same island, but the island is going away with the conveyor belt and is moving away. So that's just beautiful to see. Another very interesting thing, if we look at the mid-ocean ridge here in the Atlantic, it ends at the top with Iceland. Iceland is the mid-Atlantic ridge. It just popped out of the water because there was a very big volcanic activity. So when you go to Iceland, you're actually on the mid-Atlantic ridge, and you can actually walk in the ridge, and on your left side is the American plate, and on your right-hand side is the Eurasian plate. And you're walking in the ridge, and there's lots of activity, volcanic activity in Iceland, as we know, with the ash cloud and everything. It's going on there. You can actually dive and swim between the plates. And that's a wonderful thing. We'll see a video in a minute. You can actually dive in the middle. So let's see a few clips that can tell you everything we talked about.
But while some plates crash together, others tear apart. It happens under the ocean. Like here, in the middle of the Atlantic. Lava erupts at the boundary between two crustal plates, sealing the tear. This is the Mid-Atlantic Ridge, a 10,000-mile tear on the floor of the Atlantic Ocean. The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed. It stretches from the South Atlantic all the way to Iceland in the north, where it rises above sea level. From the air, the Mid-Atlantic Ridge is an awesome sight. This dramatic scar in the landscape marks the boundary between the North American crustal plate on the left side and the European plate on the right. The gap between ocean plates is filling in at a rate of an inch a year. Part of the restless movement of the Earth's crust that's reshaping our world.
This is a really cool footage of the vents taken by submarine.
The Earth cracks open. Fluid and minerals spew from the seafloor. Water shimmers. Life abounds. We're looking at hydrothermal vents, originally discovered near the Galapagos Rift in 1977. Basically, a hydrothermal vent is a hot spring produced by underwater volcanoes or tectonic activity. But what's really cool about them is the abundance and assortment of life that exists there. It's not life like we're used to up here on the surface. It's adapted to the dark conditions of the deep ocean. Organisms that live around hydrothermal vents don't rely on sunlight and photosynthesis. Instead, bacteria and archaea use a process called chemosynthesis to convert minerals and other chemicals in the water into energy. This bacterium is the base of the vent community food web and supports hundreds of species of animals. What kinds of animals? Well, scientists on the NOAA ship Okeanos Explorer went to the rift in 2011. And here's just some of what they saw. Riftia tubeworms, also called giant tubeworms, which can grow to their full size of almost 5 feet long in less than 2 years. Bathymodilus deep sea mussels, which are often the first creatures to colonize the vent, and are able to survive for a short time after the vent is inactive. Serpulid, or feather duster worms, and Tevnia tubeworms, which are often the food of choice for vent crabs, the top predator of the vent community.
One more little video. Wish I can do that now. So America on your left and Europe on your right. So that was the mature ocean of the Atlantic. And now we're going to go to the declining one. The declining one is the Pacific. He is declining, he is middle-aged, but he's the deadliest for life on Earth, for us humans, and for the devastation it does. Because all around the Pacific we have what's called the Ring of Fire. Most of all the earthquakes in the world are here. Most of all the volcanoes are here. Most of all the tsunamis, the deadliest ones, are here. It's a vicious area all around this very big, the biggest ocean, the declining Pacific Ocean. I mean, you can see other places around the world, but you can very, very strongly see the amount of volcanoes. Just in the last 4,000 years, look at St. Helens, how many times it fully erupted. The devastation that we see on the news usually is all from that area, mostly what we see and what we hear, the tsunamis and the earthquakes. And the question is why? So the question is why? Why is this such a different ocean from the Atlantic? What's going on? Why is it so devastating? What's different? There's still a mid-ocean ridge in the middle. And this is the answer. If we start from the left, this is something we're familiar already with. That's the mid-ocean ridge in the middle of the Pacific. And here we have the spreading of two new plates. But if we go to the right, this is where the devastation is happening. This is something new. So the very heavy iron basalt plate coming out from the mid-ocean ridge is heavy. And when it comes and meets a continental plate, because it's heavier, it goes underneath it. And what happens here is where all the devastation happens. So we've got this oceanic plate that has tons and tons of sediment on it going down into the mantle and exploding. And this here is doing all the havoc. And straight above where the oceanic plate is melting and exploding, we have the big volcanoes. But there's other things happening here. It's not only the volcanoes. If we look here, where the plate starts to go in, we have shallow earthquakes. But those shallow earthquakes are sometimes the most devastating ones, because they're very shallow in terms of where they start, but they rock everything around. So we have earthquakes right near the shore. But then about 100 miles inland, that's where we get the deep focus earthquakes, and that's where we get all the eruptions. You can see it here. The grays are all the shallow earthquakes, and the reds are the deep earthquakes into South America. And what happens actually, these mountains that we see here, they create all the huge ridges that we have all around the Pacific, all the Andes in South America, all the Sierra Nevada, the Rocky Mountains, all the mountains in Japan and Indonesia. They're all those earthquake-driven volcanoes coming from where the ocean plate goes under the continental plate and explodes. That's where everything happens. That's why it happens.
It happens because hot rock rises, heated by the Earth's core.
That's the mid-Atlantic.
Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
So, that is a very important point. This is the only place on Earth that carbon is being recycled. Carbon from the dead animals that go down from the plankton onto the seabed go into the mantle and come out in the vapor of volcanoes. Today, scientists know, and we'll see that, I think in the last slide of our lecture, that in order to really have a big possibility for life on a planet, you need plate tectonics. And we are the only planet in our solar system that has that. That's why we're so unique. One other feature that this subduction movement does are these very, very deep trenches. Not sinkholes, but trenches. They're so deep that they're actually the deepest part on Earth of the crust that goes down. And it's because the plate goes under the continent. And you can see it very, very clearly when you look at the Pacific map of the seabed. You can see that here, especially in the northwest, all the black line is a huge trench. And the deepest one is off the shores of Japan. It's called the Mariana Trench, and it's 11 kilometers deep. I mean, try and get your head around that. That's about 30 times the Empire State Building until we have some catch left. So it's very, very deep, and there's life there that we don't really know. Just a few times the Challenger submarine went down and sampled, but it's 2,500 kilometers long. It just spreads so long. It's really a big mystery, but it's very, very deep.
Why does the subduction not happen at the Atlantic Ocean?
There's a slide about that. A few slides apart. Just to go very quickly, these are things that you probably know and learned at school, but we'll see it again in a beautiful way by seeing some videos and pictures. The lava that comes out of these eruptions onshore, of course in the water, they come in different types. There's very slow ones, there's very fast ones. We'll look at them soon, and they can go up to 1,600 Celsius temperature. so it can burn anything around them. The most deadliest feature for humans is the pyroclastic cloud. That is the speed of a jet airplane. You can't run it or anything, you can't escape. And it just flows down with 1,000 Celsius temperature, full of molten rock and vibrating. You can't breathe in it, and that's what actually happened in Pompeii from the Vesuvius. Ash cloud that we remember here from Iceland, and the planes couldn't fly because these clouds are so big, miles and miles up into the atmosphere. Here you can see how, I think this is the Icelandic from Iceland, that's a red dot, and what it did all over the northern hemisphere. All this area planes couldn't fly because of little particles inside. And of course, earthquakes on land, especially in the Ring of Fire, are devastating. Now, we all know the Richter scale, but the Richter scale, mathematically, is a logarithm scale. What does that mean? That means that if I have 4 on the Richter scales, it's actually, if I have 5, it's 10 times stronger. So it goes up 10 times. So that's why when you have 4.2, 4.7, people think, oh, it's just a 4 or 5. No, it's 10 times more if it's 4 or 5. It's very strong when it goes up. A few just shots that I chose to show you about the tsunami in Japan. This is the second that the sea levee burst in the city. A second before this picture, the levee was still standing. This is the second after. And after about 3 minutes, the water came up to 3 floors of houses.
And then there's a car on there.
That's why I put the picture. If you see a car on top of a 3-story building, you can start to understand the magnitude of the water, and you can see a little shot here of people that were not so lucky. What happens in tsunami very quickly, we have some kind of earthquake, usually in the middle of the ocean or near the ridge, that provokes a very strong wave. But the wave, when it's very deep water, is only half a meter high. You can hardly see it. But this momentum and energy gets stronger and stronger as the floor of the ocean goes up, and there's less water and the energy grows. And then you get to 20, 30, 40 meter waves when they get to land. And this is the earthquake in Japan. Japan was the strongest, but we felt the tsunami also right till South America. And it wasn't devastating, but we can feel it till there. Just to show you, these are the biggest earthquakes ever recorded. We never got to 10, so 9.5 was in 1960 in Chile. 9.2 is the Indonesian one, where 230,000 people lost their life. 9 on the Richter scale was the Japanese tsunami and earthquake. And you have some examples here. So more or less all the devastating ones are in the Ring of Fire in the Pacific Ocean. Let's see some examples. This is a very slow moving lava. Okay, it moves like a few centimeters in a second, and you can just walk next to it. It's still nearly 600, 800 degrees Celsius, so you don't go near it. But this is how it moves, and you can't stop it. You can't put a wall or a fence or anything. It just moves and it takes away houses. In Hawaii, they have this all the time, part of their life. But if you compare this to the very quick ones, that's a lava flow flowing, and as you see, it started here. The road is blocked, all that was flowing, it got cooler, and in the middle it's still flowing very fast. You cannot escape that. That ruins cities and covers everything. Now imagine that's happening underwater in the ridge, and that's how things are spreading and getting built there. That gives you a bit of a sense. Pyroclastic cloud. Yes?
How come they were so close to the fire?
They were not close, it's just a zoom of the camera. I think they're about
Avalanches of
400, 500 meters away.
They cannot be outrun.
Pyroclastic cloud
It's
is
almost certain.
the most devastating one because you can't run from
They're
it.
very destructive and a major cause of death and severe injury in volcanic eruptions. They can occur at many volcanoes around the world. The high speeds, high temperature and large rocks and pyroclastic flows make them very destructive. Buildings can be set on fire, badly damaged and even completely destroyed. There are lots of examples of villages and towns being buried under the hot deposits of pyroclastic flows. The town of Saint Pierre in the Caribbean was devastated by the eruption of Montpellier in 1902. 29,000 people died instantly. Just one person survived, suffering terrible burns. The cast of bodies in the Roman city of Pompeii in Italy testify to the instant death of people caught in the pyroclastic flow.
It happens in a second. This is footage that I don't know if many of you've seen for the Japanese tsunami. It's from a police camera. This is a few seconds after the levee was burst, and the water just comes out of the levee. And it's a few minutes, a few seconds after. Look back to the junction. The junction's filling up. You're going to see fishing boats coming under the bridges in a second. It's just so fast and so strong. Here's a fishing boat coming now under the bridge. And you know, if the camera goes back in a second to the right, you can see the levee for a second, which is just now getting to be covered with all the ships that are coming in. That's one. And look at this bridge in the same town. The movement of this pole is not of the earthquake; it's only of the vast objects that are starting to run through under the bridge, houses, cars, and in a few minutes, there's just nothing left of anything. The town was just erased off the face of the earth. I will show you just one more video of some unique earthquake images. People run for safety to the middle of the square, out of the buildings, because that's the only place you can be safe. This is inside an office in Japan. We'll see a library soon. What happens to a library inside? This is a building that people are still inside. Just the earthquake is happening right when you're taking the pictures. It's still happening. There's still lots of people in these building blocks. And then the event inevitable happens. So these are, of course, the devastating consequences of earthquakes and movement of the plates. And now, to Leila's question, why do we have all that? This is the Pacific and the Ring of Fire, and this is the Mid-Pacific Ridge. And we have the same Mid-Pacific Ridge here. Whoever knows the answer, because he's a scientist, so let the people naturally debate. Why do we have the Ring of Fire in this ocean and nothing, hardly anything, in this ocean? You didn't know before, right?
No, I don't think I did.
Okay.
But I guess it's because of the lack of subduction.
And why do you think there's a lack of subduction? Why is there so? The question is now, why is there subduction here and no subduction here?
Well, because the continents are moving apart. And there's the plate edges are not around the coastlines.
Great. In this picture, you can maybe explain what you just said again. So take us through your answer, which is right.
Well, you can see the North American plate. The east edge is in the middle of the Atlantic, whereas the western edge is right at the edge of the Pacific. So there is subduction there.
In order to have subduction, which is the devastating part, you need an oceanic plate meeting a continental plate. That happens here. Here, the same plate is both the oceanic plate and the continent. There's no subduction zone in all the Atlantic. But, and this is the question, will the Atlantic start to decline? Will it start to have subduction zones at a certain point? Is it going that way? Is it the same type? As I said, this is a cycle of life. It's going in a circle, and the answer is yes, and it started already. There are 3 places in the Atlantic where subduction is already seen and found. One has just been found this 2018 here in the Gibraltar Straits. We can find that. And there's other 2. And this is actually a beautiful one that you can see on Google Maps. Go to Google Maps, make it look like not a map, make it look like a satellite, and zoom into the Sandwich Islands, which are near the south of America, Association Arc. And if you zoom into there, this is what you'll see. You see the subduction zone here on the trench, and you see about 8 new islands of, they're all just mountains of volcanic activity. You can actually see that in Google Maps if you zoom in. That's the beginning of a subduction zone in the whole devastating future. But it will take about 200 million years for this ocean to start to close up. So that's about that ocean. What I want to do, because until now we talked a lot about devastating stuff and about some things are earthquakes, and now we're going into something a bit more uplifting. Next one up, we're going to look at the toddler ocean. The toddler ocean. The toddler ocean that we're going to look at today is the Red Sea. The Red Sea that connects Africa continent and actually the Middle East or Asia. It has 2 plates on it, the African plate and the Arabian plate, and they are spreading apart. And in the Red Sea in the middle, we already have a mid-ocean ridge. Okay, 2.5 kilometers high in the middle of the ocean, and it's volcanic, and it's has lots of earthquakes and activity, has vents already, and there's even an island that came up here, I think in 2004. It came up with a volcano, and probably will stay there. So we have a real living baby ocean, like if we look at the Atlantic, how it's huge, but it started like that, and this is how it looks like, and these are just going to spread more and more, and this is how we are today, but it's just going to go on and on and on, and spread from the middle like a conveyor belt, and make Africa and Saudi Arabia go apart. We already have the magnetic symmetrical findings on each side of the ridge, so we can actually see how in the last 10, 20, 30 million years it's actually spreading in front of our eyes. So that's the young toddler, the Red Sea. One thing that we have at the end of the Red Sea, which is interesting, is this fault here. Like we have in the mid-ocean ridge, all these faults that are cracks 90 degrees to the mid-ocean ridge. They're just cracks that come because of all the pressure. They're called transform faults. That means it's not where the mid-Atlantic ridge, that's where plates come like that. It's not a subduction zone that goes like that, but it's 2 plates that are just moving along each side. We have that in the Andreas one in San Francisco. But this one here I want to talk to you about because it has a personal touch to me. This is Israel. This is Jordan. This is the Sinai Desert. This is the end of the Red Sea, which is Eilat. And this is part of one plate, and this is part of the other plate. And as I said before, if this is the ocean spreading, this is just a transformed fault on the edge of it. And when I was a student, we did some work, because when you drive down with your car from Tel Aviv to Eilat, in this area here, you're driving down to the south. On your right, it's all flat desert. But on your left, there's huge mountains that in the winter, it's all snow at the top. And there's this fault in the middle. So we went back and we found that actually these mountains belong to this mountain ridge at the end of the Sinai. It's the same ridge. And we actually found a wadi, a valley, a few valleys, here and here, with the same structure, with the same geological structure, and in 3D animation, it kind of reconstructed how they used to be together. So it's a beautiful way that you see how, in this case actually, this arrow is wrong, because both plates are moving north. Just one of them, the right one, hand side, is moving faster. So, Jerusalem here, and Amman, the Jordanian capital here, Amman is going much faster to the north than Jerusalem. That's just a anecdote. Okay, so we saw the toddler, and now we're going to go to the embryonic one, which is fascinating. When I say embryonic, we say it's in the making. It's not out yet, but it's there. and that's the African Rift Valley. So, if we see the African continent here, right in this area here on the right-hand side of the continent, there's a huge activity going on, and it's part of a subplate. It's called the Somalian subplate. And you actually go and you walk there, and what you're actually seeing in front of your eyes is the beginning of a mid-ocean ridge, but there's no ocean. Okay, we see the whole ridge starting from here till the end, all this area, with everything you need to know about ridges in the middle, but it's under your feet. You can look at it, and it's just fascinating to see. And what's happening is this part of the African plate is moving there, and this part of the sub-Somalian plate is moving to the right. And we have all of this fault on land actually happening in front of our eyes. And it looks like that. It's not yet two plates separating. It is two plates separating, but there's no ocean between them. But there is already the beginning of oceanic plate seabed floor, but there's no seabed. So already here, even if it's only a few hundred meters across, and you'll see it in the photos soon, it's already the basalt crust of an ocean plate, but it's in the middle of Africa. It looks like this. These cracks were found just in 2007 or 5, and they just crossed all over till the end, and in the middle you can actually, that's what I said, this is already oceanic basalt plate of a baby ocean that's not born yet. Okay? And it's beautiful to see when you're there, and of course it also creates these stunning land features all over. When you look with the geometric satellite system, then you can see the activity, the earthquake activity all around that region. You can actually see the future plate and where it's going to be separated from Africa. And after it will be separated, it will look like that. Okay? And let's see a few minutes. Let's show us all about that.
Ever since they were formed about 4 billion years ago. But the oceans themselves are continually changing. As the continents move over millions of years, new oceans open up, whilst others vanish. It's hard for us to grasp because it happens over such an immense timescale. Yet today in East Africa, we can actually see the beginnings of a new ocean. This long, deep fissure in an area of Ethiopia called the Afar Depression is where the planet's next ocean will form. It appeared in 2005, when the land was suddenly ripped open by a massive earthquake. Nearby, similar tears and fractures scar the desert for hundreds of kilometres. This is a continent splitting apart. It may take a few million years, but eventually these cracks will spread, and 3 giant slabs of the Earth's crust will start to separate. In time, a single crack in the desert will have turned into a new ocean.
This is how it will look like only in a couple of hundred million years.
That's not the water coming up and going over the land, that's the masses moving apart.
The mass is moving apart and the water just spills in from the ocean. So that's our embryonic ocean. Now, the terminally ill ocean. I just want to emphasize something that Tal, my wife, told me in the break. Because we talked about the mature and the declining. So the mature, if you remember, is the Atlantic spreading out, and the declining is the Pacific subduction. And the reason one is, I call it mature, and the other is declining, is because the Atlantic is still growing. The Pacific is starting to close, because the subduction zone is still a huge ocean. It will take hundreds of millions of years, but it's already starting to close. That's why it's declining. And here we have an ocean that's really at the end of his days. It's really nearly closed, and that is the Mediterranean. Our lovely summer resort. Go quickly, book your flights. It's vanishing. What we have here is actually, we're looking, this is a beautiful satellite picture, we're looking from the Gibraltar's fault, so is Morocco, this is Spain. So the plate, the African plate, is going and getting closed into the Eurasian plate. And we have a plate boundary in the middle, but only one side is a subduction zone. There's no mid-ocean ridge. That was long ago swallowed by the subduction. We only have subduction here on one side, going under Turkey, under Greece, under Italy. That's where we have all those earthquakes and volcanoes we know about in the Mediterranean. There's a big trench here called the Hellenic Trench. This is where everything's going under the continent, just like we have. But as you see, there's no mid-Atlantic ridge. There's only the other side of the same plate with the continent on it, which is Africa, coming towards Europe. That's what we have here. And when you look with the satellite systems, you can see all the earthquake activities that are vast in that area all the time. Actually, it's much more than San Francisco and those areas. This is, all the islands in Greece that you go to for vacation, nearly every one of them is a volcano, an old volcano. Some of them are still active. There's lots of activity there. And in Italy, you have huge volcanoes that we know about. We have this activity. The trench actually goes all around the boot of Italy. And here, you know what that is? Etna, that's right. And Etna, on a daily basis in the news, like they have the weather, they just say what direction the ash cloud is going today, and where not to fly and where not to go, and that's just on the news every day. And that's on the tip of Italy. Beautiful scenes, but it's still the active subduction zone devastating on that part of the Mediterranean. And the Mediterranean is going and closing. This is what happens in Turkey a lot, and in Greece, lots of very strong earthquakes, very old buildings in those cities, so it's very devastating and very strong. A little touch of British plate tectonics. There's no plate tectonics around us, except when we follow that plate boundary of the Mediterranean and we go out to the Atlantic and meet the mid-Atlantic ridge. That's the plate boundary, right? We have the European plate here, the African plate here, and they meet at the mid-Atlantic ridge. And they go out from the Gibraltar Fault, and here, if we zoom in, that spot there, that's not far from Lisbon, Portugal, in 1755, was a huge earthquake that had a huge tsunami that's recorded and written in all the history books that destroyed the city. There wasn't nearly anything left after the tsunami in Lisbon in 1755. And in the books, we have the tsunami arrive at Cornwall and devastated a few of the villages on the sea front over there. It's written, so the tsunami went over there. So that's the nearest place to us, other than Iceland that has the ash clouds, that we are affected here in the British Isles from any tectonic movement. Now, just to finish this dying ocean, it sounds awful, it's a beautiful place to go and swim, but geologically terms, it's done. Okay? What's going to happen, if you look at the map now, this is what's going to happen in a couple of hundred of millions of years. It's just going to close up. And we're going to have the Sahara touching the Alps. We're going to have Morocco and Paris on the same Champs-Élysées. If we put them one next to the other, this is how it will look like. So that was the terminally ill ocean. And the last but not least is the relic scar. It's not an ocean anymore. It died millions of years ago, but it has a huge monument for the huge ocean that was there. We have a few examples on Earth. The first one would be the Himalaya. So, beautiful picture looking from east to west. This is India here, very green and lavish, and this is Tibet in China, very barren, and it's actually a basalt plate. And we have the Himalayas here, the highest mountains in the world, with the Everest somewhere here. And what actually happened to make these huge mountains go so high up into the air? The highest point on the crust is the Everest. What goes on there? So, India has a plate of its own, it's called the Indian plate, and this is how it looks today. And it actually crashed into the Eurasian plate. And this happened many millions of years ago, 70 million years ago. India plate was much southern today, where the tip of South Africa is today. Sri Lanka is part of the plate, so it just stayed next to it. And they went up, movement with the plate, and crashed into the European plate. And it's exactly like we see the Mediterranean plate of Africa and Europe coming together now. That's what happened then. So this is, in our example now, this is the Indian plate, and this is Tibet. And there was a subduction zone. And that's what made all the Tibetan basalt plates of lava that are there today. But the minute it crashed, that's it. The subduction zone ceased to exist. The minute there's no movement, there's no heavy oceanic plate, there's only continental plate, and it doesn't go under each other, it just crashes. And when it crashes, it brings everything up. And that's why we have today a plate that's close together with another plate, and they made these huge hills of the Himalaya. And here we have the Tibetan plateau that used to be the result of everything we know today in the Andes and the Rockies, when you have a subduction zone. That's what we have today here in India. And my question is, why don't we have any volcanoes or earthquakes, nearly any of them, in the Himalayas today? There's no earthquakes or anything, Alan.
Well, if it's a relic, then it must be, from a tectonic point of view, there's no more activity. It's done its thing, and now it's set.
Exactly. So the minute these two collide, so now we have two continental plates, that stops. The subduction stops. There's nothing going on, and now it kind of comes together like two plastiline bits and just crunches together. It goes up a bit because of the pressure, but there's no activity happening here. There's no subduction zone. That's right. What other huge relic scar we know of the same kind of result that everybody knows? Alps. Yeah, exactly. So all of the Alps here in Europe, what happened is all the boot of Italy and a bit of that were a different plate. And millions of years ago, it just went up north, crashed into the Eurasian plate, crashed into the plate, and did the same thing as the Himalaya. The subduction stopped, and the Earth came together and made these huge hills that are also a relic to that. That's how it happens in India. So this used to be the volcanic area, and now it became the very high plateau of Tibet. And actually, most of the Himalayas are part of the Indian plate that crushed up. There's a beautiful video the scientists did here I want to show you. That one, 2.1.24. So they did this experiment with sand, and they put...
Right. In this experiment, we see two continents separated by an ocean.
So this is the Indian plate for our example.
Now what
and the European,
as the plates converge?
And the minute it goes down, it stops to do the subduction.
As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted.
That's how the Himalayas and the Alps were created.
Mountains. One important factor not accounted for in this model is erosion.
That's nothing to do with
Erosion exposes the deformed rocks that will...
Okay, so that was the relic star. Now, before we kind of come to the conclusion and to the summary, we've talked about the mid-ocean ridges, which are these very strong features in the middle of the ocean. We also talked about the big trenches in the area. But can you see some other very obvious structures that we didn't talk about yet that are very kind of apparent here? Can you spot them? No, in the ocean. So we have these very strange, strong lines here and here. And we want to know what those are. Just a nice ending to our talk, to talk about that. This is Hawaii, here in the middle of the Pacific. And look at the trail it has behind it. So it has this mountain range that goes behind it. And this is a hot spot. Hot spot itself is nothing to do with plate tectonic movement. It's something that doesn't move. Imagine a candle. There are about 24 hot spots in the world. These are the hot spots in the world. That's a Hawaiian one. This is Yellowstone. And what happens in a hot spot, if you imagine like a candle and the plate moving on it, the candle doesn't move. On the top of the candle, that's where you have the current volcano or the current volcanic island, but the plate is moving. So now you have a current island here because it's on top of the hotspot. The plate is moving in one direction and the hotspot stays. So what happens is you get a ridge of old volcanic islands behind the active one. So if Hawaii is here, and these are the active volcanoes, and there's a few islands behind it who are less active, and then if you go in the water, you see on the seabed, you see the whole history of it. There's already a baby island in front of Hawaii where the hotspot is already creating the next Hawaii estate, and the real estate people are starting to talk about that's only a few hundred years ago. But there's a baby island created in front of it because the plate is moving all the time. You can see here how we have the scar behind it. And that's a very good indication to us to see the movement of the plate. And there's an interesting thing because behind Hawaii it's an L shape. And about 50 million years ago, everything shifted and went the other way. And it correlates, I'll give you questions in the end of it, it will soon finish. So about 50 million years ago, something happened, scientists think it's to do with the dinosaurs, extinction, and the asteroid coming in, the big one, the Big Bang asteroid. And they find other places on Earth that 50 million years ago, there was a big shift in movements of plate. And this is a beautiful thing to see, that we see how the Pacific plate is moving from the mid-Pacific ridge here, and suddenly at this point everything changed. So we can actually see like footprints of the movement because of that scar of the hot spot. And this is a beautiful video to show you just that. Hot spot 30.
Not all volcanoes erupts to form active underwater volcanoes, or, if activity is sustained, an active volcanic island. An entire chain of such islands forms because the plate carrying the volcanoes
so the plate is moving,
stationary
this doesn't move,
inside the asthenosphere.
and then this mountain starts to be inactive and starts to go down with its heaviness, and there's a new one coming
in its place over the plume.
That's what happens when you have a hot spot, and when it's ocean floor, you can actually see the scraping, as if it's a scraping of the movement, and you can actually see and be witness to how the plate is moving. So this is how you get a ridge behind the hot spot. Now, just for a minute, back to India. Remember I told you how it moved from here and crashed into Asia. Now, do you see those two scars? This is exactly the same thing like Hawaii. So if we go, for example, for a minute to the map of the hotspots in the world, these two here are hotspots that never move. They're in the Indian Ocean and near Africa here. And this is where they are. And this is where India used to be before. So this is exactly the footprints of the movement of the Indian continent crashing in to Asia and making the Himalaya, and we can actually see the footprints with these two kind of scraping behind it. So you can actually see that very beautifully with the hotspot. So we're nearly there. We're nearly there. So we have this cycle of life that we went through that shows you, by going through it, every element of this dynamic moving Earth. So we have the rift in Africa that's starting to grow now and starting to do its first steps as a future ocean. And then we have the Red Sea, which is a toddler ocean, just starting to move. We have the mature Atlantic Ocean that's spreading out with all its glory, but little signs of rheumatism here and there. The subduction zones are starting, but he's still in his good years. And we have the declining one in the Pacific, that it's actually all over the Ring of Fire. We have the subduction zones coming in and starting to close in. We have the Mediterranean that's on its last breaths, and just a few more hundred millions of years and it's gone. And we have the relics and scars of the old ocean. And this kind of closes everything around to the beautiful cycle of this living planet. And don't forget, only 5% of the oceans are discovered and we've been there. 95% are not discovered yet. It's much more mystery than space, because in space we're already, in our solar system, we're going places, we're researching, we're getting places, we can see, as we'll see next week, we can see very far away. Here we can't see, we can't take a telescope from the shore and look to the ocean depth and see what's there. We have to actually physically go down there in order to see life, for example, on the mid-ocean ridge with the vents and all those animals. There's only 5% explored. That's a huge mystery still out there. And as I said, planet Earth, if we look at all our planets, is the only planet that has plate tectonics. We have a bit of scars of some creases on Mars, and we have one old volcanic mountain there, but that's not real plate tectonics. And what we have on Europa, which is one of Jupiter's moons, which is actually a very big candidate for potential life, are not plate tectonic. It's something entirely different to do with ice on the oceans. So now scientists really come to the conclusion that, for example, what the mid-ocean ridge is doing in terms of all the magnetic flow and the plates coming and getting born and subduction, all this movement around the mantle is actually making the magnetic field of Earth and protecting us from solar wind, because we have very strong magnetic shield. Earth has a shield from the solar wind, which is very deadly. And this is to do with all the movements on the plate. And also, what we said before, the recycling of carbon, the seabed, a few minutes, okay? The seabed carbon, the dead animals go into the mantle when the subduction happens and comes out in the plume of the volcanoes. All this recycling is very important for life on Earth. And elements and ingredients like phosphorus and sulfur that come out in the mid-Atlantic ridges and mix up in the atmosphere, that's essential for life. And when we're looking for life now in other potential planets, these are things that are taken into consideration. Does it have plate tectonic movement? Because that's essential to life. And this is the only planet in our solar system that has it. So we are fortunate to be on this one, because this is where everything happened, and it creates life as we've seen in the mid-Atlantic ridges. The vast animals that live there that we didn't even know about until a few years ago. So just to look at our planet, not only on the living creatures and the vegetation and the water in the oceans, but also as the planet itself is moving. And if you fast forward the geological process and you see Pangea moving and the continents coming and subduction and hotspots and everything, this is a live, vibrant planet that makes life happen here. So that's it for me. Thank you.